Let's now create our derivatives for inverse trig functions. Start with inverse sine of x, which of course at this stage we don't know how to differentiate. However, we do know how to differentiate the sine function. If I make x the subject, x will be sine y, and instead of finding dy dx, I can find dx dy. Differentiate sine, we know it goes to cos. There's my derivative, 1 over the cosine of y. We tend to have it in terms of x though. Let's play around with that. The cosine of y, I could rewrite as the square root of cosine squared. Cosine squared is 1 minus sine squared. Sine is what we said x was, so we get it in terms of x. 1 over the square root of 1 minus x squared. Let's do the same for inverse cos. So x becomes cos. Differentiate that, we get minus sine. Turn it upside down and play around with that. We actually get the same answer, it's just that one is negative and one is positive. What it means is if we have to integrate, say 1 on the square root of 1 minus x squared, we actually have two possible answers. I could say it's the inverse sine of x, but legitimately I could also say, no, hang on, it could be minus the inverse cos of x. Depends on what the question's doing as which one I would pick. Inverse tan then, x equals tan y. Differentiate that, we get sec squared. Sec squared is 1 plus tan squared. So there's no square root sign in this one. 1 on 1 plus x squared. So there's our three basic inverse trig functions. So to generalise that, if it's a linear function, inverse sine, I can go 1 over the square root of a squared minus x squared. But note, as far as a linear function goes, I'm talking about one where I've got a number in the denominator. I'll do some examples in a sec to show you why that could be useful. Inverse cos becomes minus 1 on the square root of a squared minus x squared, and inverse tan becomes a on a squared plus x squared. To generalise it completely then, if I have to find the inverse sine of some function, we get the derivative over the square root of 1 minus the function squared. Inverse cos, we get minus the derivative of the square root of 1 minus the function squared. And inverse tan, I get the derivative over 1 plus the function squared. So I have inverse sine of 5x, then even though it is a linear function, it's going to be easier to use the generalised form because I've just got to go, well, the derivative of 5x is 5 over the square root of 1 minus the function squared, 25x squared. Certainly if it's not a linear function, I don't really have a choice. Inverse cos of e to the x, differentiate e to the x, we get e to the x, but inverse cos is the one that's negative, over the square root of 1 minus the function squared, e to the 2x. Here is where that other form might be useful. If I've got something as simple as just x on 3, then I can just go, oh well, that's 1 over a squared minus x squared, and I get it straight away. I mean, I could do it the other way as well. It just means a little bit more working out, because the derivative would be a third on the square root of 1 minus the function squared, x squared on 9. To get rid of the fractions, I'll multiply everything by 3, which is the square root of 9 of course, and we get our 1 on the square root of 9 minus x squared. So you do get it using the other one. E to the power of the inverse cos of x. It's an exponential function that we're differentiating. So exponential function, when we differentiated that, well, what did we do? We differentiated the power. That's inverse cos, so I get minus 1 on the square root of 1 minus x squared times e, but the power did not change. Possibly a bit neater just having that on the top of the fraction. So minus e to the inverse cos x over the square root of 1 minus x squared. This one here just highlights a couple of things here. When you have inverse trig, remember, don't write it as tan minus 3x. Remember, that minus 1 is not saying the reciprocal of it. It's not a power, it's telling us inverse trig. So this is inverse tan of x to the power of 3. Bring down the power, lower the power, diff the inside, differentiate inverse tan x. We get 1 on 1 plus x squared. And just tidying that one up. Product rule. Okay, write down the first, x squared, diff the second. The second bit is an inverse tan function. Differentiate that, I get the derivative 3x squared on 1 plus the function squared, so 1 plus x to the 6, plus, write down the second, inverse tan of x cubed, diff the first, differentiate x squared, we get 2x. And tidying that one up. Okay, let's look at some HSC ideas. Function x is the inverse sine of x plus the inverse cos of x. Show that the derivative is in fact 0. If I differentiate inverse sine, I get 1 on the square root of 1 minus x squared. If I differentiate inverse cos, I get minus 1 on the square root of 1 minus x squared. So yes, the derivative does equal 0. Hence, or otherwise, prove the inverse sine of x plus the inverse cos of x is pi on 2, that result that we know. Okay, Well, what is the significance of the derivative equaling 0? If the derivative equals 0, then the function must have been a constant. As they are both continuous functions, I haven't got any issues with the domain or anything like that, so I know, yes, when I integrate this, it's just going to give me a constant value over that domain. All I got to do then is substitute a number in, and I'll find out what the constant is. So substitute in 0, we get pi on 2. So that is indeed our function. Hence sketch the function. Now this is where we have to be careful, because it's very tempting just to draw the horizontal line then of pi on 2. But we have a problem with the domain. Inverse sine and inverse cos are only defined between -1 and 1. So it's just that piece of the horizontal line. Playing with that same question, but changing it. So instead of inverse sine and inverse cos, what if it was inverse tan and inverse cot? But rather than saying inverse cot, I've said inverse tan of 1 on x. Okay? Same idea. Show that the derivative is equal to 0. Differentiate inverse tan, I get 1 on 1 plus x squared. Inverse tan of 1 on x, the derivative, minus 1 on x squared, over 1 plus the function squared. Alright, well, if I multiply in the second fraction, everything by x squared, yep, I get 1 on 1 plus x squared plus negative 1 on 1 plus x squared, that is 0. So we get the same idea. But what happens when we sketch this function? See, we have discontinuity here. See, whilst the domain of inverse tan is all real x, we've got a problem with the 1 on x. It's discontinuous at x equals 0. Now what that means is, when I substitute in the value, I have to test either side of that discontinuity. Because whilst it is a constant number, will it be the same constant number? Sub in 1, we get pi on 2. But when you sub in minus 1, you get minus pi on 2. So the mistake people would make on this one is to, like the last question, just draw the horizontal line, pi on 2. But actually, it would look something like this. Yes, when x is positive, we'll get pi on 2. But when x is negative, we'll get minus pi on 2. One a bit more recent. We've got two functions. The first one's the tan of the inverse cos of x, and this other function, the square root of 1 minus x squared over x, and they've drawn a picture of that second one for us. Show that their derivatives are the same. If we differentiate that first function, it's a tan function. So differentiate a tan function, we would differentiate it, but it changes to sec squared, and then the angle doesn't change. So we end up with, well, the derivative of inverse cos of x is minus 1 on the square root of 1 minus x squared. We're going to sec squared, and the angle stays as inverse cos of x. How on earth is that the same? If I put the sec squared on the bottom, it now becomes cos squared of the inverse cos. Well, now the cos inverse cos cancels. So I have x squared, the square root of 1 minus x squared on the bottom. Okay, let's see what happens when we differentiate the other one. Got to use our quotient rule. Square the bottom, x squared. Write down the bottom, diff the top, minus, write down the top, diff the bottom, and playing around with that, we can show that, yeah, these two derivatives are the same thing. So using part I, show that those functions are actually the same thing. Well, we just showed that the derivatives are the same. Now, it does not necessarily mean the functions are the same. You can have different functions that end up with the same derivative. It's just because you've maybe moved one up vertically or down vertically. They would still let those x values have the same slope, but they are different curves. But what we do know is that when we integrate that, because when I subtract them I get 0, when I integrate them I get a constant. For them to be the same curve, that constant would have to be 0. So when I integrate, I know I'm going to get function x minus g of x, and it's got to be a constant. So function x is g of x plus some constant. And as I say, we want to show that that constant is 0. Now when x is greater than 0, function 1 minus g of 1 equals a constant. I can substitute into that and I get that the constant is 0. But I do need to check, because again, have a look at g of x, we've got a problem with the domain. Maybe that's why they gave us the graph to highlight, oh look, it doesn't exist at x equals 0. So let's check the other side as well. And when we substitute in 0, yeah, it also turns out that the constant is 0. So it's okay. Both sides turn out to be 0. Therefore, yeah, we can say function x is g of x. Last year's paper. For what values of the constant k would this function have an inverse function. So how can we tell if things have an inverse function? Well, one of the easiest ways was the horizontal line test, if you remember, if we could see it visually. Now, of course, we can't look at this one visually because we don't know what k is, so it'd be very hard to draw this diagram. But what we also know about a curve that satisfies that horizontal line test is it's always going to be either continually increasing or continually decreasing. So I don't actually need the picture. I can use the derivative to see whether it's always increasing or always decreasing. So I differentiate that function, and playing around and tidying up, I come up with that expression. So it's going to be increasing or decreasing over its domain, of course. And the domain of this one, what have we got? Well, inverse tan of x function, that's all real x. X squared plus 1, we're not going to have any issues there. So it looks like our domain for this is all real x anyway. So in other words, the absolute value of x will be greater than or equal to 0. The bottom of this fraction is always positive, so I don't need to worry about it. It's the numerator that's going to be the key. So I'm saying the absolute value of the numerator has to be greater than or equal to 0, which means that either that expression inside the absolute value sign is less than or equal to 0, or it's greater than or equal to 0. Can't be both. It's got to be one or the other. Now what that basically means is this quadratic, because that would be a quadratic, can't have two solutions. See, here's a quadratic where it does have two solutions. You see, above the x-axis the quadratic's always positive, and below the axis it's always negative. We're saying, hey, our function is either always below or equal to 0, or always above. So that's the situation we can't have. In other words, the discriminant of this quadratic has to be less than or equal to 0. Because when it has two solutions, the discriminant was greater than 0. We say it can't happen. It's got to be the other one. We negate that, if you like. Right, let's solve that. Our discriminant, negative b, well, fortunately there is no x term here, so b is 0. So we're really just saying minus 4ac. And if we play around with that, the critical values there, minus 1 and 1, we are talking about in between those 2 points. So we get the k is in between minus 1 and 1. That was 14b. But then 14c came with this one. Also involved inverse trig and also used a similar idea. Explain why this equation has exactly one solution. So in between minus pi and pi, we're just looking at that piece of the curve. Think about an inverse tan curve where k is positive. Its derivative would be that. K on 1 plus k squared x squared. That is always positive, because remember we're saying k is greater than 0. The bottom of the fraction's got to be 0, top of the fraction is greater than 0. So again we're talking about something that is continually increasing. Well, that means the inverse tan of 3x is also continually increasing, because just make k equal 3. And inverse tan of 10x is continually increasing. Make k equal to 10. And if we add two continually increasing functions together, then that sum's got to be continually increasing as well. In other words, this is a continually increasing function, and they would satisfy the horizontal line test. So we would only have one point of intersection over the natural domain. That will only have one solution. Well, the natural domain, remember we said, was all real x. So if we're just restricting between minus pi and pi, well, it's certainly only going to have one in that section as well. Now go and solve this equation. Inverse tan, well, I'm going to tan both sides. And what we have here is the tan of a compound angle. So tan plus tan on 1 minus tan, but the tan of the inverse tan would cancel. I just get 3x plus 10x on 1 minus 3x 10 times 10x. Tan of 3 pi and 4, of course, is negative 1. Solve that equation and I get two solutions. And I think what a lot of people then did is they said, fantastic, I got the answer. But what did you just prove in part I? You proved it only has one solution, but you've come up with two solutions. One of these solutions has to be discounted. And what we know is if that theta is less than 0, then the inverse tan of theta is also less than 0. So if I'm saying inverse tan of 3x plus inverse tan of 10x is equal to a positive number, it would be impossible for x to be negative. Therefore, that's not a solution, so the only solution to this equation is x equals a half. Okay, that shall do us.